previously I introduced you to the concept of linear approximation. In this video, what we will be looking at the maths behind linear approximation. So starting off with something that we know by now thoroughly. And what is that? That is the concept of a derivative. Okay, so I know that, and you know that f dash c, okay, a derivative of function at any point c is essentially the limit as the change in x tends to 0. It's very minuscule. The ratio, we are looking at the limit of the ratio delta f by delta x, that is change in the function by change in x, okay, as this change in x tends to a very small number 0, okay. So that is actually an approximation. That is actually an approximation for derivative. So what we are trying to say is that the moment we consider the change in x is very small. The change in x is very small, and change in x is actually, change in x is very small, and x is almost the point C. X is almost the point C. So I'm going to just change what I'm writing here. So x naught, or you can call it any point C, is almost x because the change in x is too small. Okay, is too small. In that scenario, what we're trying to say is that this ratio, this difference quotient, the change in the functional value corresponding to the change in x, okay, is almost same as f dash c for any point c, or f dash x naught, whatever we might like to call it. So taking actually c as x naught, so that we are in the notation of x's, okay. So this thing implies that essentially change in f is almost equal to, I am not putting equal to sign here because we're in the game of approximation. We can't say that it will exactly be that, but it will almost be like that. So this change in f is almost equal to the product of change in x and the derivative at that point x naught, okay, the derivative at that point x naught. So what is change in f? Now what is change in f? Talking about change in f, so what do you think is change in f? So what is happening is that we were at a point, x naught, okay, then we had some change in x, so we added some, okay. So this change in f is essentially f of x naught plus delta x, and what will be delta x? Delta x will essentially be x minus x naught. Delta x is essentially x minus x naught, okay, the change in the x value, that's what is delta x. So delta x essentially will be x minus x naught. That means this and this cancel out here, okay, and what remains with us is fx minus fx naught. That is what is delta f. Delta f will essentially be this minus, this is my new point, this is my old point, fx naught. Fx naught is my new old point, and when I'm reaching a new point, I'm essentially adding a delta x out here, okay. So fx minus fx naught should approximately be equal to, might not be exactly equal, but approximately f dash x naught into delta x. Now what is delta x? Delta x is the change in x, and as we have just seen, it is essentially x minus x naught. That is what is delta x. Okay, so x naught being the old point. So this implies that fx minus fx naught is approximately same as f dash x into x minus x naught, and from there I get that the functional value at x, fx is actually almost equal to fx naught plus f dash x naught into x minus x naught. Remember that this is essentially an approximation. Let me just write it down for you. This is an approximation. What we are trying to say is that the function is approximately same as this at around x naught. Okay, this is not for the whole function. What we are trying to say is that this LHS is almost like RHS around the point x naught, Okay, we'll be looking at certain example and trying to figure out what exactly we mean. We have seen an example of logarithm, exponential, but mathematically this is what we mean, okay? And the most important case generally we will see is around 0. What is happening? What is the approximation of a function around 0? This is a very important one. Around 0 is one of the simplest case where your x naught is 0, but it's the most important thing, the most important case for that matter.